This video is intended to cover topics that we go over in the first 1 or 2 labs of the Astronomy 1100 course at Kwantlen. Generally, you don't need to watch this video if you have attended the labs. You would only watch it if you had missed for some reason. Some of the information that I give in this video will be very specific to me, Jennifer de Benedictis, so if you have a different lab instructor, be sure to clarify any questions you have with them. So to begin with, hi, I'm Jennifer. You can call me Jen, Jennifer, Ms. de Benedictis. It's really not an issue to me. Email is the best way to get in touch with me. I have given you my phone numbers for both Richmond and Surrey campus, but because I move between the 2 campuses, email is the best way to get in touch with me. Things that you should bring to the lab include a lab manual, and by the way, there is an electronic version that you can have for free from the department. Ask your lab instructor how to obtain that. You also need a lab notebook. We recommend the black ones that you can buy from the bookstore that have graph paper in them, but some lab instructors will allow you to use any lab notebook, so clarify that with your lab instructor. Also, it's a good idea to write your name along the bottom edge of your lab notebook, that is, on the bottom of the pages, along the bottom edge. This is because the notebooks get handed back in a big stack, and it's easier to find yours in the pile if you've written your name along the bottom edge. You will need a pen. We do require you to use pen in your notebook. And you want a scientific calculator, one that's capable of doing trigonometric functions and scientific notation. The calculators in smartphones are okay for this, but not really great. So if you can find a proper scientific calculator around the house, that would be better. It's also helpful to have a small ruler for drawing tables in your notebook, but that's optional. I'm now going to go over some lab policies. You can find this page in the lab manual. To begin with, the lab schedule is posted on the door of the laboratory. You should check it every week to find out which lab you should be preparing for because the labs do not run in numerical order. The labs are worth 25% of your course grade, and there is no lab exam. If you've taken the course before and you got at least 70% in the labs, then you may qualify for what's called a lab exemption, which would mean that you wouldn't need to repeat the labs. We could just give you the grade that you got last time. So if you think you qualify, go and talk to your lab instructor about it. It is something that you have to set up in person with them. It doesn't happen automatically. Scrolling down, you will be working with a partner to take data, but you each will have your own separate lab book and you'll be graded separately. The late arrival policy is that if you miss your lab instructor's introductory lecture, you'll have to work alone that week. You will not be allowed to join your partner. Also, the lab instructor will not repeat the lecture for you, so you'll have to do the experiment based on the write-up in the lab manual. You are still welcome to ask questions if you get stuck, however. Now, the missed lab policy is a lot more strict than the late arrival policy, so I want to be really clear on this. The labs are considered part of the course requirements, and you must do them all to pass the course. So I just want to repeat that. If you ditch a lab, you fail the whole course. That means that if you miss a lab for a valid reason, like you were sick, you will need to do a makeup lab. Now, the next thing I'll say is specific to me, Jennifer de Benedictis, so if you have a different lab instructor, be sure to clarify with them how they want you to handle absences from the labs. But what I'd prefer you do if you wake up and you're too sick to come to school is that you email me as soon as you can to say you're not going to make it to the lab. The default is that you would need to bring me a doctor's note, but generally speaking, if it's the first time you've missed a lab, I'll be lenient about that. However, that's something I will tell you. So if you're too sick to come to school, email me to say you're not going to make it, and I will email back to say whether or not I want you to get me a doctor's note. Also, if you know in advance that there's some lab that you can't make it to, say you have a family function to attend, come and talk to me as soon as you know the date, and we'll work something out. Now, before I move on to the topic of teaching you how to fill in a lab notebook, I'm just going to give you a little summary of what to expect in a typical lab. So every week, you would show up with your manual. Your marked work from the previous week will be waiting for you. Your lab instructor will start by giving you a short introductory talk on how to perform the experiment and any safety concerns, and then you would perform the experiment with your partner. You can hand in your notebooks and leave whenever you're finished, and the lab is due at the end of the 3-hour lab period. For the remainder of this video, we're going to cover how to fill in a laboratory notebook, and we'll review some mathematical concepts that you're going to need for this course, such as percent discrepancy, significant figures, and scientific notation. We'll now go over how to write up a lab in your notebook. This bullet list on the bottom of page 6 in the lab manual outlines what elements have to go in the lab report, but I will show you examples as we go through this. To begin with, you start on the top of a fresh page and you write down the experiment's title, the date, your name, and your partner's name. So it would look roughly like this: title, date, name, and partner's name. The next thing that goes in is the objective or goal. This is just a few simple sentences saying what you're trying to accomplish in that week's experiment. A lot of the experiments in the lab manual have a goal in them, and you're welcome to copy that. Again, this is what it looks like, just a simple sentence saying what you're trying to accomplish in that experiment. The next thing to include is references to any outside materials that you used, like a website or a textbook. Usually you don't need to include anything because the only thing we're using is the lab manual. The next thing you do is you perform your experiment and record your data. Now, one thing that I'm very picky about is that you need to label everything fully. Here's what I mean. In the procedure section of an experiment in the lab manual, you'll see numbered steps. So step 10, do this, step 11, do this, and so on. It's very common when students are writing up their experiment to just write down step 10 and then the calculation or the data, step 11 and then the calculation or the data. This isn't enough. You have to label every calculation and set of data in words. The number by itself is not enough. Likewise, when you write down a single item of data, make sure you label it in words, not just the symbol, and every number should have its units written down with it. That's just part of complete labeling. And while I'm here, I'll just point out that in your lab notebook, you have to show every calculation. So you need to show every calculation in full detail. Even if it's a really simple calculation, like one number minus the other, don't do it in your head. You do need to write out the full calculation in detail for your lab instructor to see. Now, when you have repeated or related trials, you probably want to record your data in a data table, and there's an example of this on the next page of the lab manual. So here's the example, and as you can see, it's got a nice informative title, and all of the information that we would have written down for a single item of data is now written down in the table heading. So they label the measurement in words, they put down the symbol, and the units. Now you'll remember that I told you had to show every calculation you do. In a table, if you've got a column where you're doing the same calculation on every row, you only need to show one sample calculation. So the rest of them you can just fill in the numbers, but you do need to show one sample calculation for one of the items in that column. Now going back to that bullet list in the manual, the last thing that you put in your lab write-up is an analysis of your results, but I'm going to defer talking about what goes in the analysis until after I've told you about the concept of percent discrepancy. Before I do that, though, I'd like to first talk about one last thing having to do with your lab notebook. A scientist's notebook is a legal document. It's supposed to be a permanent record of all their work. And in order for your lab notebook to be a permanent record of your work, there's a couple of rules we need you to follow. They all basically boil down to the idea of never obliterate information from your lab book. So to begin with, you must write in pen only. You can use pencil for graphs, but generally speaking, your lab notebook has to be written in pen. Second, you should never tear pages out, you should never use whiteout, and you should never scribble something out to the point where it can't be read. If you need to make a correction, put a single line through the error and then write the correction nearby. The point is that both the error and the correction are still readable. Remember, your lab book is supposed to be a permanent record of everything you did, including mistakes, so even the mistakes should still be readable. Another thing you should be aware of is that you should never write data on a piece of scrap paper with the intention of then copying it into your book neatly later. All of that work should go directly in the book as part of your permanent record of your work. So if you do want to do some rough work, just put it on the back of a page and label it rough work, and your lab instructor will ignore it when they're marking. So rough work is allowed as long as you put it directly in your lab book. And finally, I just want to assure you that messy is okay. Your lab book can have things X'd out, comments in the corners, arrows running all over the place. It's okay if it looks messy. All we care about is the quality of the science. So don't spend any time trying to make your lab book look perfect. Just make sure that it's readable and complete. In the sciences, it's very common to want to compare two values to see how well they agree with one another. And one of the ways to do this is by calculating what's called a percent discrepancy. The formula for doing this is given in your lab manual here. You subtract one value from the other value, ignoring any minus signs that crop up, and then you divide by what's called the best value and multiply by 100 to turn it all into a percentage. The definitions for what's the best value are given below the formula. If one of your values is an accepted value, that is, it appears in scientific literature or you've got some reason to trust it more than the other one, if one value is accepted, then that's what you use as your best value on the bottom of this formula. However, if both of the values are measured values, things that you measured, and you've got no reason to trust one of them more than the other, then you calculate the average of those two values, and that's what goes in the bottom of this formula as your best value. So here's an example of that. You've got two numbers, and you want to compare them to each other to see whether they agree well. So you start calculating the percent discrepancy. You take one of the values, and you subtract off the other value from it. But then comes the question of what should be your best value. Now, if both of these were measured values, then I would take the average of the two, and then I'd use that as my best value on the bottom of the expression. However, one of these is actually a known value, which means that that's the value we should be using as our best value on the bottom of the expression. Note that the known value appears both on the top and the bottom of the percent discrepancy. So then we calculate our percent discrepancy, and what does this value actually mean? Well, the point of a percent discrepancy is that if the two values are in good agreement, that number is going to be small, and if the two numbers are in poor agreement, it's going to be big. The benchmark that we use in this course is 10%. So if the percent discrepancy is 10% or less, we say that our two values were in good agreement. If it's more than 10%, then we say that the values were in poor agreement. This gets used in your lab write-ups analysis section. So the very last thing that goes in your lab write-up is your analysis section, where you summarize your results and say what they mean. There's generally only 3 things that you need in your analysis, so I'm going to go to a handout now which summarizes these. The first thing you put in your analysis is a summary of all your important results. These often come in pairs, a theoretical value that you calculated and a measured value that you're going to compare to the theoretical value with a percent discrepancy. The example here is based on the parallax experiment, which you will be doing this semester. So to summarize their results, they simply say the measured distance to the ball using the tape measure was this value, and the distance to the ball using the parallax method was this other value. So they just summarize their important results. If your two values were compared to each other with a percent discrepancy, then next you would list that percent discrepancy and explain whether it indicated good or poor agreement between the two values, which is what they've done here. They say the percent discrepancy was 1.35%, that's less than 10%, therefore our two values are in good agreement with each other. And the last thing you include is to say what that good or poor agreement means. So often the conclusion you can draw from good agreement is that the technique that you use to take that measurement is accurate. And that's what they've done here. They say because our two numbers are in good agreement, this means that the distance to an object can be accurately measured using parallax. So in summary, the 3 things you need in your analysis are, first of all, to list your important values, and if you compared any of those values with the percent discrepancy, to list the percent discrepancy, to say whether it was good or poor agreement, and then to say what that good or poor agreement tells you. When you take a measurement, the thing to realize is that there's no such thing as a measuring device that has infinite accuracy. And for this reason, science has developed a way of writing down numbers which shows you how precise a measurement the measuring device you are using is capable of giving. Look at the 2 scales on this page. They both have a pointer that's pointed to the same location on the scale, but which of the 2 scales do you think is going to give you a more accurate number? Probably the second one, right? It's got more tick marks, and that means that you're going to be able to estimate where the pointer is located a little more accurately on that scale. The rule of thumb that we're going to use is that you write down everything you can read off of the scale plus one estimated digit at the end. So for that first scale, the pointer is between 2 and 3, and you would write down everything you can read off of the scale, 2 point something, and then the last digit is the one that you estimate. So you might write down 2.8, where the 8 is your estimated digit. On the second scale, we can see that the pointer is located between 2.8 and 2.9. So we'd write down everything we're sure of, 2.8 something, and then the something would be our estimated digit. So I would write down 2.84, where 4 is my estimated digit. And by the way, it's totally okay if you estimate that last digit a little different than somebody else. That's the nature of an estimate. At the bottom of this page, there's an exercise. So I want you to pause the video here and write down what you think the pointer position is for each scale to the correct precision. Okay, have you got your answers? Now compare them to mine. So I think the pointer position on this first scale is 7, where 7 is my estimated digit because there are no tick marks between 0 and 10. For the second scale, I think that the reading is 6.9, where 6 is what I read off the scale, and 0.9 is my estimated digit. For the third scale, I think the reading is 6.89, where 6.8 is what I was able to read off of the scale, and again, the 9 at the end is my estimated digit. So now we'll scroll to the next page, and there's another exercise here that I'd also like you to do. So this is exactly the same as before, and the only thing I'll add is to say that 0 can be an estimated digit. So again, pause the video here and write down the pointer position for each scale to the correct precision. Got your answers? Okay. So I think the reading on the first scale is 7 again, where 7 is the estimated digit. On the second scale, 7 is the digit I can read off of the scale, so 0 would be my estimated digit, 7.0. On the third scale, I can clearly see the difference between 7.0 and 7.1, so 7.0 is what I can read off the scale, and I put another 0 at the end of that for my estimated digit, so 7.00. Now all of these numbers that we've written down, they're called significant figures, meaning that they're scientifically significant. They were based on an observation. In the next part of the video, we're going to be talking about how you deal with significant figures when you're doing a calculation. In other words, how you round off values correctly. When you do a calculation, sometimes your calculator gives you a whole bunch of digits, and the question is, how many of those should you round off? Because you don't want to lose information by rounding off too aggressively, but you also don't want to imply you had more precision in your experiment than you actually did by leaving too many digits there. So there are some rules for determining how many significant figures you should keep on your final answer when you do a calculation. There are two rules, one for dealing with addition and subtraction, and the other for dealing with multiplication and division. I'm going to show you the one for multiplication and division first. So when you have two numbers, and you want to multiply or divide them, the rule is that you count up how many significant figures each of the two numbers has, and whichever number has the fewest significant figures sets how many significant figures your answer is allowed to have. So for example, this top number has 1, 2, 3, 4 significant figures. The bottom number has 1, 2 significant figures. That means the final answer is only allowed to have 2 significant figures. So if you plug this into your calculator, it will give you this number. However, we still need to round this off to have only 2 significant figures. And you do that like this. You either write it as 4600, where the two zeros are placeholder zeros, they don't actually count as significant figures, or you can use scientific notation to just write down the two significant figures, 4.6 times 10 to the 3. I'll be discussing scientific notation next in this video. When you want to add or subtract two numbers, the rule is different. Instead of counting up how many significant figures the two numbers have, you instead count up how many decimal places they have. So this first number has 1 decimal place and the second number has 0 decimal places. And that sets how many decimal places our final answer is allowed to have. So the final answer is only allowed to have 0 decimal places. So plugging this into your calculator gives you this value, and then you want to round it off to have 0 decimal places, like this. 5 or higher rounds up, 4 or less rounds down, so we get 262. Now for this rule, I can actually explain why we're rounding off like this. Remember that the last digit is always the estimated digit. That means we're unsure about whether this 5 is exactly a 5, and that uncertainty translates down to this 5 in the answer. Likewise, we're not sure that this 9 is exactly a 9, and that uncertainty translates down to the 1 in the answer. And if we're unsure whether that 1 is really a 1, then there's no point in writing anything that comes after it. So we round that off so that we only have one digit in the final answer that's an estimate. And I'll leave you with one final case, and that is that sometimes your calculator gives you too few digits. So this is the addition-subtraction rule. That means we count up how many decimal places the two values have, and both of these have 1, 2 decimal places. That means the final answer is also supposed to have 2 decimal places. So in these cases, do pad the end of your answer with zeros. Scientific notation is a way to write very large and very small numbers in a very compact fashion. It's also less ambiguous to write some numbers in scientific notation, because remember, a 0 can be a significant figure or it can be a placeholder 0 that just shows you where the decimal place is. So when you write something in scientific notation, if a 0 is a significant figure, you write it down, but if it's a placeholder 0, you leave it off. So scientific notation relies on this trick, that if you write down 10 raised to the power of some number, you start to see the following pattern. 10 raised to the power of 0 is 1. 10 raised to the power of 1 is 10. 10 raised to the power of 2 is 100. 10 raised to the power of 3 is 1,000. And 10 raised to the power of 4 is 10,000. So this is a very compact way to keep track of powers of 10. Because if you've got 10 raised to the power of some number x, it's always going to be 1 with x zeros after it. So as I said, scientific notation is for writing really big and really small numbers in a very compact fashion. And this is good because astronomy has some very big numbers. So here's one. This is the speed of light in meters per second. To write this in scientific notation, the first thing we want to do is locate where the decimal point is. And it's located here at the end, and now we're going to count how many spaces over we have to move it to put it right beside the 3. So 1, 2, 3, 4, 5, 6, 7, and 8. And so to write this in scientific notation, we write 3.00 times 10 to the 8, where the 8 is because we moved the decimal point 8 spots over. And by the way, the reason why we have 3.00 written here is that these two zeros are significant figures. That's the correct accuracy for the speed of light. The other zeros were just placeholder zeros. They just told us where the decimal point fell, so we left them off. So now let's write a very small number using scientific notation. Again, we start by finding the decimal point, and then we count how many spaces over we'll have to move it to put it right beside the 1. So here's our decimal point, and we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so we would write this as 1.84 times 10 to the negative 12, where it's negative 12 because we moved the decimal point 12 spaces in the other direction. So now we'll talk a little bit about how to type values in scientific notation into your calculator, because your calculator has a scientific notation button that makes it really easy to do this, and if you don't use that button, then you have to be very careful to always put brackets around your values that are in scientific notation. So it is easier to learn how to use your scientific notation button on the calculator. This page is in your lab manual, although it's sort of hidden away in part B of the density experiment, and it explains how you use the scientific notation button on your calculator. So first of all, dig out your calculator and look at it. What company makes it? If your calculator is made by Sharp or Hewlett-Packard, look around on the button pad for a button that says EXP. If your calculator is made by Casio, you want to look for a button that says EXP or times 10 to the X. And if your calculator is made by Texas Instruments, look around on the button pad for a button that says capital EE. That's your scientific notation button. So if you want to type a value in scientific notation into the calculator, say for example 7 times 10 to the power of 4, then the way you do it would be to type 7, then your scientific notation button, then 4. And that's it. Depending on the make of your calculator, your display might read 7 and then a very small 0, 4 in the corner, but that means 7 times 10 to the 4, even if it doesn't look like it. Now, if you hit the equal sign, most calculators will automatically convert that number back to standard notation, which means if you typed in 7, scientific notation button, 4, and then hit the equal sign, it should convert it back to 70,000. The bottom of this page has some exercises that I do recommend you try out with your calculator, just to make sure that you are using the scientific notation button correctly. So to begin with, type in 2.97, scientific notation button, 3, and then hit the equal sign. Your display should now read 2,970. So pause the video and try that now. When you're done, try typing in 3.76, scientific notation button, -3, and then hit the equal sign. Your display should now read 0.00376. Again, pause the video here and try this out on your own calculator. And if you're still having trouble getting it to work, do consider asking a lab instructor to show you this. This page of your lab manual introduces some new units that we use in astronomy. We're going to be doing some exercises later in the video that make use of these, so let me introduce you to them now. The first new unit is called the astronomical unit, and that's defined as being the distance from the Sun to the Earth. So we are 1 AU away from the Sun right now. An AU is defined as being 1.496 times 10 to the 8 kilometers. It's a good distance to use when you're measuring distances within our solar system, but it's a little too small for measuring the distances to stars. The second unit you've probably heard of, the light year. It's defined as being the distance that light travels in 1 year. A light year is a little too big to measure distances within our solar system, but it is good for measuring the distances to stars. The symbol for it is LY for light year, and a light year is defined as being 9.46 times 10 to the 12 kilometers, so it's quite a bit larger than an AU. The next unit is the parsec. This is a unit that astronomers actually made up for doing parallax measurements so that they wouldn't have to do a conversion of units. The symbol for a parsec is PC, and 1 parsec is defined as being 3.09 times 10 to the 13 kilometers, so it's roughly 3 times larger than a light year, and thus it's also a good unit for measuring the distances to stars. And the next quantity that I'll introduce is the speed of light, 3.00 times 10 to the 8 meters per second. Now coming back here to the manual, if you scroll down to the bottom of the page, there are some questions. I'm going to go over 3 of these with you, and they make use of the units that we just learned about. However, all of them involve a units conversion. So before I go over the questions, we're first going to learn about how you convert one set of units into a different set of units. So the questions we're going to go over involve things like converting parsecs to light years. But before we go into complicated things like that, let's start very simple. Say you've got a quantity in centimeters and you want to convert it to meters. Now you probably know that you can just move the decimal point 2 spaces over, but I want to discuss how to do a conversion formally. When you do a conversion, what you're really doing is you're multiplying your number by a fraction that you make out of two other numbers. And before we talk about what those two numbers should be, let's first talk about what the units in the fraction should be. What I want is for my final answer to be in the units of meters, and that means I want the units of centimeters to cancel out and go away, like this. So that means I want the centimeters to be on the bottom of my fraction, so that they'll cancel out with the centimeters in my original number. And then I'll only be left with meters on the top of the fraction, which means my final answer will also be in meters, which is what I want. So now that I've figured out what the units on the two numbers in my fraction are supposed to be, I now need to figure out what the values should be on the top and the bottom of the fraction. Well, these two numbers just get built out of an equality. How many centimeters are equal to 1 meter? There's 100 centimeters in 1 meter. So in my fraction, I write 100 centimeters equals 1 meter. So now we've created our conversion factor, which is this fraction. So now you can type this into your calculator and get the answer for how many meters is in 45.7 centimeters. And this gives us the answer that we were expecting. So now let's try something a little more complicated. Say you've got a value in meters per second, and you want to convert it to kilometers per hour. So this is actually a two-part conversion, meters to kilometers and seconds to hours. So let's convert the meters first. We start creating our conversion factor, which is that fraction of two numbers again, and then we think about the units. Because remember, we want our final answer to be in kilometers. That means we want the meters in the original expression to cancel out. So pause the video for a moment to think about this. Where should the meters go in our conversion factor? Top or bottom? If you said that they should go in the bottom, then I agree with you. Because by putting meters in the bottom, they should cancel out with the meters on the top in the original expression. So now we just need to fill in how many meters are in 1 kilometer. And that's 1,000. So 1,000 meters equals 1 kilometer. And now you can plug this into your calculator and see what the answer is supposed to be. And that's 4.573 kilometers per second. Of course, we're not done yet because we still want to convert seconds into hours. So I'll bring my value down here, and then we'll start assembling the conversion factors for that. Now we're going to go from seconds to minutes and then from minutes to hours. So I actually need two conversion factors here. And we still need to think about how the units are going to cancel out. Because we've got seconds on the bottom of the original number, that means we need seconds on the top of the first conversion factor. Otherwise, the units won't cancel out properly. Likewise, we're going to need to cancel out the minutes also. The minutes appear on the bottom of the first conversion factor. That means we want to put them on the top of the next conversion factor. Then they'll cancel out. So again, the seconds in the bottom of the original expression cancel out with the seconds in the top of the first conversion factor, and the minutes in the bottom of the first conversion factor cancel out with the minutes in the top of the second conversion factor. And then all you should be left with is kilometers per hour, which is what we want. So how many seconds are there in a minute? There are 60 seconds per minute, so we fill that in. So how many minutes per hour? Again, there are 60 minutes per hour, so we fill that in, and now you can type this in to your calculator and find out what the answer is. 4.573 times 60, divide by 1, times 60 again, divide by 1. And the answer is 16,462.8 kilometers per hour. Or we can write this in scientific notation in order to give it the correct number of significant figures, which would be 1.646 times 10 to the 4 kilometers per hour. And this is a good time to point out something you may not have noticed, and that is that constants don't affect the significant figures. In other words, 60 is a constant, 1 is a constant. They don't affect how many significant figures my final answer is allowed to have, only the original value did. So my original value only had 4 significant figures. That means that my final answer is only allowed to have 4 significant figures. But the constants, 60, 1, 1,000, they don't affect that. Going back to the manual, there's these 4 questions, and your lab instructor might assign some of them to you for grades. I'm going to help you get started on 3 of these. I won't solve them for you, but I will give you the final answer and show you how to get started with each of them. They're all based on unit conversions, which is what we were covering in the last section of the video. We're going to start with question 3 first, because it's actually the easiest of the 3. Question 3 is, if a wavelength of light is given at 5.894 times 10 to the negative 7 meters, how many nanometers is that? So this is a conversion from meters to nanometers. So as always, you start with your value, and you want to multiply it by a conversion factor. Notice that they've given you the conversion factor up here in the question, so your main task is to figure out what goes on the top and what goes on the bottom of that conversion factor. Remember to think about what you need the units to do in order to wind up with an answer that's in nanometers. Here's the final answer that you should get, so pause the video now and work out the solution to this question on your own. The next question I'll have you work on is question 1. How long is an astronomical unit in light minutes, where a light minute is the distance that light travels in 1 minute, and remember, an astronomical unit is the distance from the sun to the Earth. So they're basically asking how long does it take sunlight to reach Earth. So to put the question very simply, 1 AU equals how many light minutes? That's what they want you to calculate. Now what makes this question hard is that we don't know what the conversion factor between AU and light minutes is. If we did, we'd already have the question answered. So we're going to have to do a 3-step conversion to get the answer to this question. We'll have to go from AU to kilometers, and then from kilometers to light years, and then we'll have to step it down from light years to light minutes. So a 3-step conversion starting with going from AU to kilometers. Luckily, the lab manual already told us how many kilometers are in an AU. So we'll just write down the definition we got directly from the lab manual. 1 AU equals 1.496 times 10 to the 8 kilometers. So that's our first conversion, and now we want to go from kilometers to light years. So we multiply our value by a conversion factor, taking care to make sure that the units are going to cancel out correctly. And now you can put in values for your conversion factor and calculate how many light years is equal to 1 AU. Remember that your lab manual told you how many kilometers are in a light year. Also, keep in mind that the value you calculate here should be a really tiny number, just because light years are so much bigger than AU. Once you've got that value, you need to do your third conversion, where you take light years and step it down to light minutes. You're going to do this by multiplying by 3 conversion factors. The first one converts between light years and light days, taking care to make sure the units will cancel out correctly. The next conversion factor will convert from light days to light hours, again with the units canceling out correctly. And the third fraction converts from light hours to light minutes, again with the units cancellation. And that should give you your final answer for how many light minutes are equal to 1 AU. This is the answer you should get, 8.31 light minutes. In other words, sunlight that you see on Earth is about 8.31 minutes old. So pause the video now, work out this calculation yourself, and make sure that you're getting the same answer. The last question I'll have you solve is question 4. How many centimeters is equal to a light nanosecond? In other words, how far does light travel in 1 nanosecond? Now there's a trick that makes this question easier to solve. The trick is to realize that when they ask you how many centimeters light travels in 1 nanosecond, another way to phrase that would be to say that they're asking for what the speed of light is in centimeters per nanosecond. Because centimeters is a distance, nanoseconds is a time, distance divided by time, that's a speed. So the easiest way to solve this question is to start with the speed of light in meters per second and then convert it to centimeters per nanosecond. And obviously that's going to be a 2-step conversion, from meters to centimeters and from seconds to nanoseconds. And note that in the lab manual, they do give you the conversion factor between nanoseconds and seconds. Here's the answer you should get, 30 centimeters. So in 1 nanosecond, light travels about the length of a ruler. This is the last part of the video, so work this last question out on your own and make sure that you're getting this same answer. Good luck with the course this semester.